I'm Harvey, and I'm professor at Chalmers University of Technology in Gothenburg, Sweden. So Chalmers, together with our technology transfer company CIT, was to have hosted the live version of the conference, but things turned out differently, as we all know. I would like to say the good morning or good afternoon. I realize we have attendees from all over the world, so not quite clear what time it is, but it is 12 o'clock exactly in Gothenburg in Sweden. So yes, my name is Simon Harvey, and I have prepared and managed panel 4 related to technology, processes and systems with my colleague Anna Realini from the consulting company RSE, located in Milano, Italy. Do you want to say a few words of welcome, Anna? You're unmuted, so you need to unmute yourself.
Yeah, sorry. Hi, everybody. Welcome. As Simon said, my name is Anna Realini, and I work for actually for a public research body in Milano called RSE. Welcome, everybody, and I leave the floor to Simon that will be chairing today's session.
Okay. Let's see if we can move forward. Yeah, there we go. Move backward one. There we go. So to this first session is related to heat pumps. And I think it's a very interesting session. We have 4 papers to be presented, and they will be, well, they're all focusing on advanced heat pump solutions, of course, but they're basically taking very different perspectives. We have some more top-down studies looking into opportunities. That will be our first paper from Australia. And then we have some case studies from one case study from AIT in Austria, which is also looking at some case studies in drying applications. We have a more technology oriented and then technology performance assessment from Olvondo Technology in Norway. And then we also have some considerations about a more general study of opportunities for heat pump integration in drying processes. So I think it's time to get going. I think you know the rules of the game, that we will take the presentations one at a time. I think we will allow, if there are any brief questions related to clarification of something, we will take that immediately after the presentation. But the idea is that the Q&A, the general discussion for all papers, will be handled at the end of today's session. So I am going to now hand over the floor to our first speaker or speakers. We have Jon Jutsen from the Racefor2030 from Australia, with his colleague Jarrod Leak from the Australian Alliance for, let's see, something hiding there, for energy productivity. So I will hand the floor over to you, Jon and Jarrod. Please go ahead.
Thanks very much, Simon. You can hear me okay?
Yes, we do. Yes.
Thank you. If we can go on to the first slide, I can control, I think. Can I control? No, nothing's happening. I'm trying to page down and it's not paging down.
Yeah, I do no longer have control there, Jon, so I think Carol has to handle this one. Yeah.
There we go. Hopefully that was me doing that. Yeah, so we're doing a little double act today. This is because I currently head a new research institute called the Reliable, Affordable, Clean Energy Cooperative Research Centre. But previously I was the chief executive of the Alliance for Energy Productivity. And so Jarrod's got that role now, and he's taking over the work that we were doing on heat pumps for industrial applications, because we saw that there was enormous opportunity for improving energy productivity and for reducing carbon emissions using heat pumps instead of typical fossil fuel central heating systems. So just a quick word about about Racefor2030. It's a new cooperative research centre. It is in Australian based. We have some members from Europe, which including Wuppertal Institute and one other who I will look up, Potsdam Institute, who are just finalising paperwork with them, but they're going to be members. And we have a very large membership base that looks right across the energy value chain, enabling us to do some very interesting work where we can look at solutions which are needing the input from multiple players along that chain. So we go all the way from end users all the way back through research institutions, state governments, technology companies, all the way back through to the networks. We're very much focused on the end user and end use energy productivity. And we have programs in 4 basic programs, and one of those is in business, which is one of the major programs. And we have a program on decarbonising process heating. We're by the way, fairly well funded. We've got probably $350 million or so of resources will be going into the CRC over the next 10 years. And some of that will be going into decarbonising process heating. The first stage of our work is going to be focused on process heating up to 150 degrees. And later we'll be looking at 300 degrees and then open. We're going to be putting out an opportunity assessment to do a study on process heating opportunities up to 150 degrees, which will come out in the next few weeks. And there's a requirement that the opportunity assessments include an international partner. As I said, Wuppertal and Potsdam are both partners that can participate. So going on to why we got excited about heat pumps. I've been working in the industrial sector for about 35 years, thereabouts, and it always disturbed me greatly the amount of energy waste in process heating, particularly centralised boiler-based process heating. Firstly, because most processes there isn't a good understanding of even what temperature is required to do the process, but then the actual activity of centralised process heating with the reticulated steam and condensate. Most sites have no idea what their thermal efficiency is. They can't measure efficiency. Many don't even measure the fuel in, but no one has a good idea of how much heat actually goes to the process. And this is just a quick look at the losses across the system, but many boiler and steam systems, if you looked at the energy in compared to the energy that actually goes into doing useful work in the process, quite often the efficiency is as low as 35%, and generally less than 60%. So we got very interested in the idea of localized, much more efficient heating using heat pumps. The slides have decided to stop moving again. That's interesting. Yeah, I can't move the slide now. It's not moving at all. Carol, you might have to jump in and give me a hand here. Because the slides have stopped moving. Yeah, I know I've got control, but nothing's happening. That's the problem. It was working fine before, but it stopped working. Carol, could you take control and move the slides on, because I can't. Okay, thank you. So the other reason we got very interested in this whole area is because of We did another project on Industry 4.0, the digitalization and digitalization of manufacturing. And there's a trend that's accelerating, which also brings with it great energy productivity benefits, to go to a digitalized and modularized manufacturing, which is very responsive to end user needs. And again, this doesn't line up very well with a central steam system. We've got very poor control and no modularization. Next slide. So we got particularly interested where, rather than just looking at a heat pump to replace an individual process application of process heating, we saw that there would be particular advantages if we could replace all process heating with either localized heat pumps or non-thermal processes, or alternatively an electric boiler at worst case scenario. So we looked at applications like the one here, where you could replace the entire process heating system, and that's where you can get rid of the losses in the steam distribution system. Next, please. So just a quick summary before I hand over to Jarrod. We saw heat pumps having a great opportunity for improvement in overall productivity, and as well as the energy efficiency of processes in manufacturing, because of the direct reduction in energy costs, and the size of the benefit depends on the relative electricity and gas price. Obviously, the higher the gas price and the lower the electricity price, the better the heat pump economics. The coefficient of performance, which is somewhat related to the rise temperature in many cases. The ability to recover waste heat, particularly taking low-grade heat and upgrading it, or also using latent heat from dryers. Another speaker will be talking about this later. And also the opportunity to potentially do heating and cooling from the same heat pump using both sides of the circuit. Being able to displace the entire centralized steam system has huge benefits through cutting a lot of those distribution losses. Many process benefits, including reliability, improving dry quality, and exposure of workers to heat, and increased controllability and modularization, reduced carbon emissions, and finally, through being able to be much more suitable for Industry 4.0 integration, because you can modularize and you have much more control. So the overall cost benefit for many companies we saw as being very beneficial now. And so we got very interested in getting a whole series of projects done to identify where the opportunities would be. And Jarrod's going to talk to you a little bit about the more detailed applications, as well as the project that we have undertaken over the last few years to have a look at the feasibility in many applications of heat pump applications. Over to you, Jarrod.
Thanks very much, John. So quite a timely day to be talking about heat pumps. I understand Elon Musk has done a tweet today. Maybe you asked him to do that, John, about heat pumps, saying that Tesla's likely to get into heat pumps in future. So a good timing for discussion. So yeah, I'm the CEO from A2, what's known as A2EP in Australia. So we are a non-for-profit organisation funded by members, and helping Australia double its energy productivity. And it says I'm controlling. And so looking at quickly at the cost benefit there for heat pumps. And this is a analysis that was carried out in Australia here. And on the left axis, you've got dollars per gigajoule. And then through the lines, you've got cents per kilowatt hour for electricity. And on the bottom, they're looking at the degrees of heat lift there. And you'll see just how incredibly cheap the heating costs can be using a heat pump, especially especially when you've only got, say, 20 or 30 or 40 degrees of heat lift, and you've got a very cheap electricity. It certainly comes through with a very low cost heating option. And talking of cheap electricity, we'll get a little bit to that later. When we talk about heat temperature lift, that is what the waste heat is at. So if it's ambient at 30 degrees compared to the temperature that you want to achieve. You want to achieve hot water at 65 degrees and you had an ambient of 30 degrees, then that's a 35 degree heat lift, temperature lift on that one. So we've looked at many different applications that the heat pumps can be used for. I understand we're going to talk about a bit more of those with other presentations, but these are sort of the main generic ones where we start looking at drying and food washing and what have you. You can see down there pasteurization, a very big one, because you can cover both heating and cooling, so a very interesting application for heat pumps. But yeah, certainly a big range of applications that we looked at through Australia, but a lot of them in food and beverage where we've done the studies for. When you talk about decarbonisation, I think it is important to note and just quickly touch on that it's not just all about heat pumps. For decarbonisation, there's many other technologies as well. We've certainly seen examples where a pulsed electric field there is being used, and certainly ultrasound processing, centrifugation and microfiltration is really quite common to reduce the carbonisation load and remove things like evaporation. So it's certainly not just heat pumps, but we certainly see heat pumps has got a very big part to play in decarbonisation. If we take an Australian context here and we look at the total energy consumption, and I actually did a bit of a check on general European type of consumption, and oddly it comes out rather similar. 44% of energy usage in industry, 40% for transport, 16% for buildings. We have that very large chunk for industry, fuel used for heat. And in Australia, a lot of that is in natural gas. You see that 48% there. That was different when I compared to some data there in Europe and elsewhere. But yeah, still a large percentage of it was in fossil fuels. If you took that heating demand, or actually it's actually the heating production, and broke that into the temperatures and what it's needed for, you see a very large chunk is in that sort of 250 degrees and above, and that's certainly not in the heat pump range. In this bottom 40 or so percent, 250 degrees and below, that is within the heat pump range. Often you'll have a steam boiler producing steam at 10 bar or so, and that would then have registered in that 150 to 250 degree range. But that steam may be used just for pasteurization at 80 degrees or so. And so that could definitely be done with a heat pump as well. So we look at something like 30% of process heating can be done with heat pump technology. There was a very good report done in Australia summarising all this information. I understand some similar things have been done in Europe and the US as well. If we look at a bit of a comparison here on the left, you've got the process heating options there by sector in Australia. And they, again, very similar overlap with Europe, food and tobacco with lots of low temperature options, as does paper, as does wood. I won't spend too long on those. Uniquely for Australia though, Australia's adoption rate of solar PV is at the fastest in the world, and we are now having regular events of negative electricity prices during the day. That is wholesale prices, not what consumers would see or industry would see. But this is where we're headed in I think it's 2 out of the 6 major industrial states. This is the case, and you'd expect within another year or so, virtually every state in Australia is seeing negative electricity prices. And this really does create a massive opportunity for heat pumps, where they can be coupled with thermal storage and be used during these negative electricity events to take advantage of extremely low prices. In terms of another enabler, let's say, for heat pump technology being adopted, we're certainly seeing the supplier capability growing. Here's a list of heat pump suppliers, and these are mainly coming from Europe, of heat pump suppliers that are doing a high temperature. Now, I could have listed for lower temperature heat pumps a lot more suppliers, but these are the ones doing the high temperatures. And you see the very high temperatures, say 130 and above, is mainly done by refrigerants, which will not likely to be phased out. But certainly when it comes to ammonia and CO2, the natural refrigerants up to 120 degrees, no problems at all. A bit slow. Very quick summary here, a lot of information, but you can look at this slides no doubt later, and you'll see if there's something in light blue, and if I focused on food and beverage distillation, you see a lot of that in light blue or blue, and that is very easily done with a heat pump. If it's in red there, some high temperature drying, say in paper or milk drying, things like that, still a little bit out of the range of a heat pump. Not to say that a heat pump couldn't help a lot with preheating in each of those applications, but you'll see there's a very long list of applicable applications for the heat pump as well. Just quickly then, I think we might be in a little bit short in time, so I'll mention the program that was run very successfully in Australia by the Australian Renewable Energy Agency, and this is a program of identifying opportunities in the market, helping sponsoring of pre-feasibility studies to the tune of around 10 or 15,000 euros, and then seeing that sponsored further into a feasibility study, one-for-one match dollars with the client. And then ARENA looking at funding up to, I think it was 50% of these projects. So it's certainly gone very well received process, and we're seeing a huge build of interest and capability with engineering consultants of how to run these processes and how to investigate where and how to use heat pumps. It's been a really good process, and I think would welcome to share how that process worked with other organisations around the world, that's for sure. These are the sort of main projects that were done with the inside this program, and you can see some very big, large savings of gas in the tune of 80,000 gigajoules for one vegetable processor, and down to something like maybe 10,000 gigajoules per annum just for wine production. They don't use a lot of heat there. So this program was run across a wide range of industries, and we certainly anticipate this is going to be setting the standard and setting a lot of benchmarks for heat usage and decarbonisation, certainly within these industries. And just to finish off with, just in the essence of time, here is one operating example of an abattoir in South Australia where they're using, they've displaced LPG boiler using a high temperature heat pump to help them with their water for sterilisation and other wash down waters. So fantastic savings there, very good paybacks, and an excellent way for decarbonisation. We expect that only to certainly grow over the next couple of years after these programs have been run. Good. Happy to leave it there. I think I imagine the slides will be distributed, so there should be plenty of good information to share there for everybody going forward.
Okay, thanks, Jarrod and Jon. It was great setting the scenes there, and it was nice to get the Australian perspective. Of course, you were presenting lots of conditions which I think are similar for many parts of the world. So I think, because as you said, we are running out of time, or we have run out of time, so I think we'll move straight into the next presentation, and we'll take general questions at the end. So I would now like to invite Veronika Wilk from AIT to present her work about high temperature heat pumps for industrial processes. And I know you have an application to present in the brick kiln industry, brick drying. So the floor is yours, Veronika.
Thank you very much for the kind introduction, and it's a great pleasure for me to participate today in this online conference. And I will give you a short update on the dry efficiency project, our demonstration project for high temperature heat pumps. And before I jump into the results from our demonstration site, I will give you a brief overview on the situation in Austria in general. And I will just try to move the slides somehow. Oh yeah, okay. Now it's moving. Okay, perfect. So in Austria, industrial heat pumps are gaining more and more importance, and there's a statistics that is published every year where they also count the number of industrial heat pumps that are in operation. And so far, there are about 300 installations. There are three main areas of application where we find those heat pumps. So the most important one is the food industry. Their heat pumps are used for heating and cooling, and those installations usually have a capacity of several 10 to 100 kilowatt, and the heat that is supplied by the heat pump is usually reused within the company. So it's either used for space heating to heat the production halls or for process heat. Another important field of application are power plants that provide heat for district heating. And in those installations, we find heat pumps for flue gas condensation. So they use the heat pumps to recover the latent heat that is still available in the flue gas to increase the fuel efficiency of the power plant. And the third group, which is also gaining importance, are heat pumps that make use of industrial waste heat and also supply district heating. This is mainly due to the fact that district heating has a lower temperature range than the industrial process itself. Those installations usually have heating capacities in the megawatt range, and they supply heat with temperatures in the range of 60 to 95 degrees C. So whenever we use a heat pump in industry, we usually replace fossil fuels by electricity. And in Austria, electricity is rather green. So currently 75% of electricity is provided from renewable sources. And the aim for 2030 is to reach 100% renewables for the electricity consumption. And if you're interested in this topic, I can also advertise a presentation by another colleague from EIT, Roman Gaya. He will present on Wednesday how to supply the Austrian industry with 100% renewable energy. So that's just a teaser, but now we will just jump into the high temperature heat pumps. And I will speak about our demonstration project, Dry Efficiency. So within this project, we develop high temperature heat pumps that are able to supply process heat at 160 degrees C. We focus on drying processes within this project because drying processes require a lot of energy and they're usually carried out with fossil fuels. Within the project, we develop three different heat pumps. Two of them are closed loop heat pumps that are used for drying with air. And the third heat pump is an open loop heat pump, which is used for steam drying process. So the open loop heat pump is a mechanical vapor recompression system, and it will be used in a sludge dryer. And on the pictures below, you see the three demonstration plants. We are currently, so we have already started one, and the other two are still in the commissioning phase. So this is now a really exciting phase of our project. And in my presentation today, I will focus on the one demonstration site that is already active, which is the one for brick drying at Wienerberger. So it is one of the closed loop heat pumps, and this is a basic scheme how a closed loop heat pump works and what were the main questions within our research project. So we have an industrial application. We have two demonstration sites for the closed loop heat pump, as I mentioned already. Wienerberger, the world's largest brick producer, is operating one of the demo sites, and the other one is at Agrana, an Austrian food company, where they use the heat pump for the drying of starch powder. So at both industrial sites, we have waste heat sources available with temperatures in the range of 80 degrees C, and they require process heat with 160 degrees C. And one of the most important parts of the heat pump is certainly the compressor. And within our project team, we have two compressor manufacturers. It's Bitzer cool machine in Bochum, Germany. They provided a modified screw compressor to the project. And the second compressor technology that we are looking at is provided by Viking Heat Engines, now Heat AS. They supply piston compressors that are suitable for high temperature applications. So a lot of development work was done on the compressor itself, but also on the lubricant. We have a lubricant specialist within the team, it's Fuchs Schmierstoffe, and they developed a lubricant that is compatible with the refrigerant, and it's supposed to be stable at the high operation temperatures. As the refrigerant, we use Option MZ from Chalmers. It's a synthetic material. It's R1336MZZZ, which has a low GWP value, which is very important to come up with an environmentally friendly solution. And this is how the brick drying process looks like. So basically the bricks are formed, then they are dried, and then they are fired in the kiln to reach the final stable product. And we focus on the tunnel dryer, which is shown in the lower part of the scheme. And so the bricks are moving through the tunnel dryer in a continuous process. And the drying air within the tunnel dryer is heated with those heating surfaces that are also shown here. The heat for these heat exchangers is supplied by waste heat recovery system. This is a thermally driven heat pump, making use of energy from the kiln and also from the exhaust air of the dryer. And this thermal heat pump provides hot water with 90 degrees C. And our dry efficiency heat pump also uses this water cycle as the heat source. And this heat pump provides a higher air temperature for the final drying zone to really ensure that the product properties are met in this final zone. So basically, the dry efficiency heat pump acts as a booster on the existing system, and it also replaces a natural gas burner that can be used for this purpose. This demonstration plant has a thermal capacity of 400 kilowatts, and it's not integrated directly in the airstream, but with an intermediate circuit. This is mainly for the reason of the research project, that we can measure all the properties in a very accurate way. So we can measure the heat supply temperatures in the water circuit and then feed in the energy into the tunnel dryer. And yeah, here I have some impressions from the construction and assembly work of the heat pumps. So on the left, this is the, in front you see the module consisting of 4 piston compressors provided by Viking Heat Engines. And in the picture on the right, there's a compressor in green. That's the screw compressor from Bitzer. And the heat pump itself is designed as a container module. So it was manufactured on the site of our manufacturer, and then it was transported to the brick factory, lifted into the factory via the roof, and it's located on top of the tunnel dryer on a platform, and there it was connected to the process. We started the commissioning work in November last year, and then we did a rough trial operation to test the functionality of the heat pump, to test all the controls and really see how the heat pump behaves within the process. And within this trial operation, we tested different heat supply temperatures ranging from 110 to 160 degrees C. And in this diagram, that should come up right now. Yeah. You see a summary of the trial operation. So we have here on the x-axis the temperature lift, which is the temperature difference that is overcome by the heat pump. And on the y-axis is COP. This is the ratio of the thermal energy that is provided by the heat pump and the electricity consumption of the heat pump. And the red squares show the results of the trial operation. So we reached a COP of 4.7 for a heat supply temperature of 120 degrees C. and a COP of 2.7 at the highest temperature of 160. In this diagram, you see also a lot of blue dots. I have taken those dots from a publication from Gordon Abergaus. He compiled the efficiency data of a large number of industrial heat pumps in this publication. And those are market available heat pumps. And so in this diagram, we can compare the efficiency that we have reached during trial operation with those that are already available, although they are not operated at such high temperatures. And yeah, we see that the dry efficiency heat pump is among the most efficient devices, which is a very nice result to start from. The line in this diagram indicates the COP of a heat pump, of an ideal heat pump with a second law efficiency of 50%. This is just to get an impression how the COP changes with increasing temperature lift. Yeah, and another important aspect about our project, or basically for the implementation of heat pumps in general, is the techno-economic assessment, and to really see the consequences when you change a natural gas burner into a heat pump. So this comparison is just a comparison of the heat pump and a natural gas burner providing the same amount of energy. In this comparison, we have not included the dryer or the whole brick production process. So this is something we're still working on. On the left side, you see the values that we used for the natural gas. So the CO2 emissions coming from gas combustion and also the gas prices. Those are values for Austrian industrial companies, averaged values from last year. And on the right side, there are the input values for the heat pump, so it's for the electricity. And as I've mentioned, electricity is rather green in Austria, and this is why the CO2 emissions from the use of electricity are lower than the CO2 emissions coming from natural gas combustion. What we've also included in this assessment is a CO2 price. So the current CO2 price that was taken here was the one from March when I wrote the paper, with 24 euros per ton of CO2. And then we looked also into an increased CO2 price with 50 euros per ton, which is, well, double the current price, but still not a very high value. And those are the results for energy reduction and CO2 emission reduction. So on the x-axis, we have again the heat supply temperature from 120 to 160. And at 120 degrees, more than 80% of CO2 emissions and energy can be reduced. And at 160 degrees C, the reduction is still more than 65%. In terms of costs, the situation is a bit different. The blue line shows the current energy costs. At 120 degrees C, it's a reduction of about 50%. And at the highest temperatures, the value reduces to 10%. If we take into consideration the CO2 price, the reduction potential increases dramatically, especially for the high heat supply temperatures. So with an increased CO2 price, we have more than 30% of cost reduction for the 160 degrees C. And this is also a strong motivation why a CO2 price can allow technologies to be put into the market when they help to save CO2. And finally, there's a comparison of heat pumps and other direct electric systems. So as we've seen before, of course, there's a strong dependency of the efficiency of the heat pump on the temperature lift. So on the temperature difference between the heat source and the heat sink. And at one point, it might be more useful to use a direct electric heater than a heat pump. And this is what is shown in this diagram. So we have again this the line for the ideal heat pump with 50% second law efficiency in gray. And whenever the COP is higher than the black line, energy cost reductions are possible with the Austrian prices that I've shown before. So in our case, if the temperature lift exceeds 85K, that the cost will be equal and no more savings are possible. But if we only look at the end energy savings, there is far more potential to use the heat pump, because the threshold when the heat pump does not allow for energy savings compared to electric heater is given here in blue. So there's a huge lift possible. And if we compare it to the natural gas burner, that's the red line. And it also shows that in this temperature range given here, the heat pump always allows for end energy reductions. So I'm already at the end of my presentation, and I'd like to sum up what I've shown you today. So we did a successful commissioning of the first dry efficiency heat pump at Wienerberger. We reached a 160 degrees C heat supply temperature with a very satisfactory COP. And the heat pump allows for significant CO2 and energy cost reductions compared to natural gas. Demonstration projects such as the dry efficiency project are a very important step to establish new technologies in industry. So our project will still go on for another year, and we will use this year to roughly test the heat pumps, and also to start the two other demo sites that I did not mention today. And we will also use this time to learn more about the stability and the operation experience in this industrial process, to really know if this what's the potential of the technology, what should be optimized for the future, where are open questions that still remain after the project, and to get to know the technology better. There's a large multiplication potential for industrial heat pumps, so the concept that I've shown you here can be basically applied for all other processes that have waste heat available and that require process heat up to 160 degrees C. So there's a huge potential in the food industry, but also in the paper industry or chemical industry. And last but not least, I'd like to introduce you to AIT's dry efficiency team. So it's a very complex and big project, and it's of course not only one person working on these questions. So I'd like to thank the team for the good collaboration, and I'd like to thank you for your attention, and I look forward to your questions. Thank you.
Okay, thanks a lot, Veronika. We do have one question, which I think is clarifications, which I think maybe you can handle directly. We have a question asking about the emission factor of the Austrian electricity mix, which you use to quantify the difference compared to natural gas. Do you have an answer to that one?
Yeah, so I just go back to the slide. If I can make it, yeah, it's moving. So the emission factor for electricity in Austria was 285 grams per CO2 per kilowatt hour when you use electricity. This is the value that was published last year. And the one for, so it's the Federal Environmental Agency that, that calculates this value. And for CO2, it's 271 grams per kilowatt hour. So I hope this this is the answer to the question.
Okay. Yeah. Good. Yes. Okay. Well, I think we should move on. Thanks a lot, Veronika, and I'm sure we'll get back to you when we have the general Q&A at the end of the session.
Thank you.
Yes, so I think we will now move on to our third presentation, Tor-Martin Tveit, and you will be talking to us, let me see this, about high temperature heat pumps as well, and you'll be talking more about assessing the environmental impact, and particularly the global warming perspective. So a little more of this carbon factor in your presentation. So Tor-Martin, I'll hand it over to you.
Yeah, thank you, Simon. My name is Tor-Martin Tveit, as Simon said, and I'm going to present some ideas about how you can evaluate the environmental impact of a high temperature heat pump. To summarize, it's complicated, and it's I'm working for a company developing heat pumps, high temperature heat pumps for the industry. And we always get this question about what's the savings, what is the impact of CO2 emissions, and it's not that easy to answer. And I think that's kind of the history why we wrote this report. And I wrote it together with my co-authors, Omar Khan and Ron Zevenhoven, which are from the University, Åbo Akademi University in Finland. Let's see, I'll go to the next slide. We are having an EU-funded project together with the pharmaceutical company AstraZeneca, where we're going to install one last prototype of our high-temperature heat pump at the research center in Gothenburg. So it was a pity in many ways why we couldn't be there. But hopefully this will be fine as well. A little bit about our heat pumps. They are high temperature heat pump, and they're kind of a different technology from what I would call a regular heat pump. We are using helium as a working medium, so we don't have any evaporation or condensation of the working medium, which makes our heat pump quite flexible when it comes to temperatures. For this application that we're going to install at AstraZeneca, it's we're going to use waste heat from about between 40 to 50 degrees centigrade, and we're going to lift up to 10 bar steam. So we're generating 10 bar steam. We also have other applications for generating steam at 7 bar, and also hot water at 120 degrees. And hot water at 120 degrees, we also made ice water at around 0 degrees. So this is kind of the background. The rest of the presentation is not really about our heat pump. It's more general about the how you calculate the efficiency, or how you can look at the different ways of how the environmental impact of the heat pump. So I will present the first part, and then my co-author Omar Khan will present the last part. One way of looking at it is to see that, okay, we're going to replace some fossil fuel or some other kind of fuel that's being combusted in a boiler with a heat pump that's going to use electricity. So you could say that, okay, at what part, at what COP, so the efficiency of the heat pump, does it make sense to have a heat pump? And below that, maybe it just makes sense to burn the fuel directly in the boiler. So if we look sort of briefly on the graph on the left side, we have this dotted line which represents kind of the break-even point where you have to be a COP higher than the dotted line, depending on the thermal efficiency of your electricity production. So for example, if you have natural gas in Finland, so they're quite efficient with a efficiency of about almost like 50%. You can manage with a COP lower than 2. Then again, if you go to the average fossil fuels in Sweden, these are reasonably old data for the efficiencies, but I don't think they have changed very much in the recent years. But just be aware of that the details are in our paper. Again, so if you would have the average fossil fuels for Sweden, then you would almost have to go to 3 COP before you have a break-even point. So this will be assuming that the electricity is kind of one-to-one with the fuel, so that you are replacing fuel directly that could otherwise be used like directly to burn. So that's kind of a simplified way of looking at it, since the electricity mix is now quite different, and it's kind of moving to a more greener area. So this is the European average generation mix for electricity in 2018, and we can see that combustions if you look at fossil fuels, is this red part here on the left. There are also some renewables, which are like biomass, basically combustion. But then we have these other parts like wind and hydro, solar, and nuclear power, which has a very low emission of CO2 or other greenhouse gases. So it will be perhaps a bit too simplified to look at that just by comparing the COP and the efficiency of the power plant. So if we look more in detail, I'm using our heat pump as an example again. So one installation that we have, we're replacing a natural gas boiler. And during a year, the natural gas boiler was emitting about almost a little bit south of 400 tons of CO2 per year. And then based on the data from 2014, that's the blue bars here, looking at, okay, if we look at the, this is installation in Norway, so it's the Norwegian energy mix, then there will be a quite substantial emission reduction. Then again, if we have the Norwegian power system and we're looking at electricity that you just buy off the grid without a guarantee of a region, then we actually see that the heat pump would not contribute positively, so it will be an increase in the CO2 emission. Also in 2014, the average electricity mix in the EU will also cause almost the same sort of a slight addition to the CO2 emission by installing the heat pump. If you look at natural gas for 2014, then there was a reduction. Now, as I said, the trend is toward a more greener electricity generation, and you can see this quite clearly in these 4 years from 2014 to 2018. There's a substantial reduction if you compare these two bars. So then again, then we have a positive contribution of installing this this heat pump, especially so if you look at the Norwegian or the Swedish electricity mix. Then I'll go to the next slide. Another way of looking at the impact of the heat pump is to look at the exergy or the exergy losses. This is something that's not usually reported anywhere, but it's you can look at the energy flow in terms of its ability to generate work. So what we would say is a useful energy. And for heat, it's quite easy. It's like the Carnot efficiency. Electricity is just pure exergy. So for a heat pump, we're adding just pure exergy in form of electricity and some low exergy content from the waste heat and generating a reasonably or higher heat, higher temperature heat with a higher exergy. Chemical exergy is a bit more complicated, but you can sort of convert the energy that's stored in the electricity that's released during the combustion into the form of exergy. And if you do that and compare the heat pump with natural gas and oil boiler, you can see that the exergy generation, or sorry, the exergy losses for a heat pump will be less. So in that case, it would be beneficial to install a heat pump. This obviously depends on the temperature that you can produce with the heat pump, as higher temperature heat also have a higher form of exergy. I will then leave the floor to my co-author, Umara, that's going to finish with the LCA. I was a bit quicker, sorry, I was also going to go through but let's Umara go through the think, Omar, you are muted.
Hi. Hi. Yes, so I will continue with the description for life cycle assessment, which we carried on for the high temperature heat pump. So to assess the environmental impacts, we conducted this life cycle assessment using CIMA Pro 8.3 version. And in this study, we involved the cradle to grave life cycle assessment and of the technology and compared it to the conventional heaters like oil-fired boilers and then natural gas-fired boilers. In this following figure, we can see the life cycle assessment system boundary which we used for high temperature heat pump. And as it can be seen from the figure that it involves construction phase where the manufacturing and procurement of raw material was involved. And then the operation phase, which is for 1 year, use. And then the decommissioning was not involved for this study. Yes. Yes. The impacts which were associated with the technology it was characterized in 4 categories, which were human health, ecosystem, climate change, and resources. The figure on the left shows the environmental impacts which were associated with the construction of high temperature heat pump and also with the operation for 1 year. For high temperature heat pump, the primary emission source which was leading to the impact was the emission of zinc to the air, which was mainly stemming from the copper production, which was used in electrometer. The figure on the right shows the comparison of the impacts which was associated with the high temperature heat pump, natural gas boiler, and an oil boiler. As we can see from the figure, that the choice of working fluid was one of the contributing factor in determining the environmental performance of the system. Among all the categories, the human impact is the largest contributing categories by these heating technologies, which is followed by climate change. The unit process with the most significant direct emissions are the process in which fuels are burned, and the largest impact which were arose from oil boiler followed by natural gas fired boiler. The emissions which were with the highest influence are beside carbon dioxide, sulfur dioxide, and particulate emissions. That is, if we use the right finger and we make an assessment for the comparison of the environmental performance of different technologies, heating technology, we can see that high temperature heat pump is more environmental favorable than oil boiler and also natural gas. A further study has been done for the same life cycle assessment, a detailed study which also involves the comparison of the technologies for 1 year, for operation of 1 year, 8 year, and then 15 year, including the decommissioning phase. And it can be accessed at the following link, and it was recently published in Energy. for the further questions about the technology, they can be directed at this following email address of Tor-Martin Tveit. And yes, that's the conclusion of this presentation. Thank you.
Okay, thank you. Unfortunately, the quality of your connection was very bad at the very end, so we didn't quite hear you properly, but too bad. But time is moving on, so I would like us to move straight ahead to our final presentation for this session. So Takenobu Kaida, you are from the Central Research Institute of the Electric Power Industry in Japan. And you're going to be talking also about integrating heat pumps into drying processes. Hand the floor over to you. Please go ahead. Takenobu, you need to unmute your mic. We cannot hear you. So please unmute yourself and turn your camera on if possible.
Okay.
Yes, so we didn't hear you, so you should start over. Yes, okay, please go ahead.
Okay, sorry. Heat pump is recognized as one of key technologies for decarbonization in industry. Much of final energy is used for heating purposes, but a large part of them is wasted through heat losses. Heat pump has two positive coupled effects. One is energy saving by recovering the waste heat, and another is CO2 emissions reduction by using low carbon electricity as the driving power. Among various industrial heating processes, drying process is a highly energy intensive process. According to some reports, drying process accounts for 10 to 25% of total industrial energy consumption in most developed countries. But in many cases, waste heat is not recovered, or even if waste heat is recovered, the heat recovery is still limited to air preheating by heat exchanger. Recently, some high-temperature heat pumps have been developed. This allows to consider heat pumping technology for a wide range of dryer applications. Most of existing drying processes use burner or steam boiler as the heating equipment. Generally, the burner and boiler have about 90% thermal efficiency, but the steam use and efficiency is not so high. Sorry. Japan Electro Heat Center surveyed the actual condition of steam supply system. At the average value of 29 factories, the boiler system efficiency was 54%. Not only combustion loss of 10%, heat loss from piping of 25%, and heat loss from drainage of 10% are revealed. The left figure shows the existing plant image. Boiler is located far from heating processes as a centralized system. This offers easy handling, but energy inefficiency. Long steam piping causes heat dissipation. The right figure shows the replacement by distributed heat pump. This system can reduce heat transfer loss from piping, and this system can utilize waste heat from each process. When we simply replace boiler to heat pump, at the same location, the energy efficiency effect depends only on heat pump COP compared to boiler equipment efficiency. But this replacement by distributed system has a greater effect than the simple replacement. This slide shows typical two types of heat pump cycles and their development trend. One is subcritical cycle and another is transcritical cycle. The subcritical cycle is used when the heat sink temperature grade is small. Generally, the temperature grade is below 10 Kelvin. So this cycle is suitable for circulation heating system, such as keeping a room air temperature or keeping a tank water temperature. On the other hand, the transcritical cycle is used when the heat sink temperature grade is relatively large, because the heat transfer irreversible loss from refrigerant to heat sink can be reduced. This cycle is suitable for one-through heating system. In many cases of drying processes, the transcritical cycle would be better because the heat sink temperature grade is relatively large due to heating fresh air. Regarding the development trend of transcritical heat pumps, now in Japan, hot water supply heat pump up to 130 degrees C and hot air supply heat pump up to 120 degrees C are market available. In Europe, hot water supply heat pump up to 110 degrees Celsius is market available. And in Japan, two manufacturers are developing high temperature heat pumps up to 200 degrees Celsius. Also in Europe, some projects are developing high temperature transcritical heat pumps, mainly targeting drying processes. In this way, the development of high temperature heat pumps have been progressing steadily. By the way, what heat pump supply temperature is the best? 100 degrees C, 150, or 200 degrees C? This study estimates the optimal heat pump supply temperature and the effects by heat recovery using a simple thermodynamic modeling. As shown on this figure, we assume the second stage heat recovery system with heat exchanger and heat pump. First, the heat exchanger recovers sensible waste heat from dryer. Next, the heat pump recovers the latent heat. Burner or steam is used for the backup. The burner efficiency is assumed at 90%, and the steam efficiency is assumed at 54%. I explained the outline of the heat recovery system by using psychrometric chart. Here is an example in the case of starch drying air at 175 degrees C and exhaust air at 75 degrees C. The left chart shows the existing system without heat recovery. First, a fresh air of state point 0 is heated by burner or steam. The heated and dried air of state point 3 is supplied to dryer. The air becomes humid and the air temperature decreases. The exhaust air of state point 4 is wasted to the ambient. Next, the right chart shows the heat recovery system. The heat exchanger recovers the sensible heat of the exhaust air from state point 4 to state point 5. Then, the heat pump recovers mainly latent heat from state point 5 to state point 6. We can see the exhaust air at state point 6 approaches the ambient state point 0. And the heat recoveries can reduce the heat load of the heater from state point 2 to state point 3. In this study, the heat pump supply temperature of state point 2 is changed, and we investigate the optimum point. From this slide, I explain the calculation method. Regarding heat pump, we assume transcritical cycle because the heat sink temperature glide, delta TH, is relatively high, and the heat source temperature glide, delta TC, is small because of latent heat recovery. We correlate the COP using simple temperature lift, T2 minus T5. The right figure shows the performance data of EcoShirok and Transpac. EcoShirok is a commercialized CO2 refrigerant transcritical heat pump by Maekawa. And Transpac is a R32 transcritical heat pump under development by EDF. The correlation is produced by the data of EcoShirok. This correlation also agrees well with the Transpac. The correlation is valid for temperature lift up to 90 Kelvin. When the temperature lift exceeds 90 Kelvin, the efficiency is set to a fixed value of 0.71. Regarding drying condition, we collected operation data of dryers based on literature survey. 6 dryers were identified provided that the hot air temperature was below 200 degrees C and the heat balance and the water mass balance can be calculated. I will show the result later. At that time, I will explain mainly starch drying. And finally, I will explain the 6 materials together. Next, key factors related to energy different from country to country. This study assumes the condition in EU, in France, and in Japan. We use the available latest data. The CO2 emissions factors of EU and France are taken from statistical data from 2016. The other factors are taken for 2018. Natural gas is assumed as the fuel or burner or boiler. Regarding the CO2 emissions factor, the factor ratio of electricity to gas is in France is the smallest because of high nuclear power ratio. The primary energy factor ratio in EU is the smallest. Energy unit price ratio in France is smallest, but the electricity price is still relatively higher than natural gas. From this slide, I will explain the results. The left graph shows the influences of heat pump supply temperature on the heat pump heat supply and the COP. As increasing the heat pump supply temperature, the heat pump supply increases, but the COP decreases. So an optimum temperature would exist. As shown in the right graph, the heat supply contribution by heat exchanger accounts for 25%, regardless of heat pump supply temperature. When the heat pump supply temperature is 19 degrees C, the heat pump contribution is only 20%. But when the temperature is 175 degrees C, of course, all of the heat supply can be covered with heat pump and heat exchanger. This slide shows the CO2 emissions compared to existing system. The left graph is the case that the the existing heater is burner. The right graph is the case of steam. First, the heat exchanger can reduce the CO2 emissions of 25%. Then, the effect of heat pump depends on country and heat pump supply temperature. The reduction is the most in France because of the low carbon electricity. As shown in the left graph, when the reference is burner, 175 degrees C supply heat pump is not effective in Japan. On the other hand, when the reference is steam, CO2 emission reduction effect can be obtained even if the steam boiler is completely replaced with a heat pump. Okay. Next, when the reference is steam boiler, not only CO2 emissions, primary energy consumption and energy cost are described. Optimum point is defined as the heat pump supply temperature, which minimizes the energy cost. In France, the energy cost reduction effect is saturated from 150 degrees C. The energy cost is the smallest at 175 degrees C. If there is no difference in initial costs between 150 degrees C and 175 degrees C, it is better to operate the heat pump at 175 degrees C. At this condition, the CO2 emissions can be reduced by 95%. So it's almost decarbonization. Next, in Europe, the optimal temperature is 130 degrees C. At this condition, the CO2 emissions can be reduced by 60%. Also in Japan, the optimum temperature is 130 degrees C. At this condition, the CO2 emissions reduction is 50%. Sorry. Finally, the results of 6 materials are shown. Here, we focus on the specification and the performance of heat pump. In these 6 material dryers, we can see that the required heating capacity of the heat pump is less than 1 megawatt. The dryer of nori seaweed is the smallest, less than 70 kilowatt. However, we should note the capacity depends on the production. On the other hand, the dryer of nori seaweed shows the highest COP because of the smallest temperature lift. Let me summarize my talk. Recently, the developments of high temperature heat pumps have been progressing steadily. As increasing heat pump temperature, the applicable process range expands, but the COP decreases because of larger temperature lift. This study clarifies the optimum heat pump supply temperature and effects by heat recovery using a simple thermodynamic modeling and rough calculation. As a result, compared to existing natural gas-fired steam boiler system, in France, the optimal temperature is 175 degrees C. In EU and in Japan, the optimal temperature is 130 degrees C. And I understand when applying a heat pump to an actual drying process, other various factors must be taken into account, such as corrosion resistance of heat exchanger or the strategy in the case of batch operation. However, I hope this study's theoretical result will be helpful for future heat pump developments and heat pump selection as one guide. Thank you.
Okay, thanks a lot for that fourth and final presentation for this session. I think a number of you are picking up the Q&A. You have the Q&A tab there in your participant screen. So I think it's easiest if we if you put all questions to us through the Q&A tab there. But I think we had a first question, Anna, which been out there for a while, and that's to those of you who'll be presenting some work which is actually related to case studies. The question we got is a little discussion, reflection about common issues when you want to change your system to heat pump solutions for drying. So some practical thoughts. And I thought about that when you showed Veronika, when you showed your container. So that was a nice package solution which could essentially be lifted into place. So maybe you could start there, Veronika, by commenting a little on that. And don't forget to unmute yourself.
Okay, yeah, right, it's working. I'm not sure if there's a general recipe how to do that, but what we learned in our industrial projects is that it's really important to consider the space conditions, because most of the current heat pump projects are retrofitting projects where the heat pump is integrated within existing infrastructure. So there might be a very nice solution from a thermodynamic point of view, but there's still the built reality around it. So this is usually the first step of a heat pump project. It doesn't really depend whether it's about a dryer or something else, to really make sure if it can be realized within all the boundary conditions that they have. And another thing especially for drying, I would say, and I think this is also something that Takenobu touched in his presentation, it concerns the heat source. So a very nice heat source for to make a dryer more efficient is the humid exhaust gas that is released from the drying process. And usually you find in there not only the water vapor that you want to condense, but also particles and other contaminants. So I think it's also very important to think about how to design this heat exchanger and how to really take out the heat there, and also optimize the temperature level of condensation.
Okay, so your heat pump would be also delivering other benefits than just the energy efficiency benefit you're saying as well, but yeah. I think being the condensate. Okay, Tor-Martin, since you've also been involved in some real-life applications, do you want to add anything to that?
Well, not really. I think that was a quite good summary. Also, for our case, it really doesn't matter where the heat comes from already going. We prefer to have water circulating in our internal heat exchanger, so we will, in any case, need a closed loop. So it's depending on what kind of heat exchanger technology and what sort of technology is available to extract the heat and then transfer it to the internal heat exchangers.
If we move over more to policy and maybe going over to policy or grid issues, moving over to Jon and Jarrod there. You mentioned, which I think a lot of people mention when they're talking about the benefits of electrification. For decarbonization, you mentioned the high degree of intermittent renewables, which is ends up with very low or even negative electricity prices during certain periods. What's your take in Australia? I mean, the other side of that is, of course, this requirement of building out the electricity grid capacity to actually handle that. For many people to take advantage of that, you need a much different, a much stronger electricity grid, and that is likely to show up in the grid costs at the end of the day. What's the Australian perspective on that?
Maybe I'll make a couple of quick comments and then I'll hand over to you, Jarrod. I think there's two issues here. One of the things that we did in our project is we required that that participants in the project find a renewable source of electricity. So complete decarbonisation was required, but that could be either through PV in their own facility, or it could be through buying a power purchase agreement, which in Australia, the power purchase agreements for renewables significantly lower than the cost of at the moment of buying grid electricity, fossil fuel based electricity. So there's no, rather than use the grid average, we actually required that that participants actually do include renewable supply, and that didn't significantly worsen the economics for the project. Another thing that's worth mentioning is is load management and load flexibility. It's important with these projects to look at storage of either hot water or cold water, where it's possible. Obviously, the drying is not so easy, but using thermal storage to enable a use of heat pumps without dramatically increasing the peak demand of for electricity grid.
Okay, great.
I think the only thing to add to that maybe is on the electricity grid in Australia. There's some regions where the grid's holding up very well with 70–80% renewables, like in South Australia, and without too much loss factors from those renewable energy suppliers. So it is holding up okay, but it's definitely hitting limitations now. There's some huge investments in the pipeline there for several states to get the electricity around a lot easier, a lot better, and that's been recognised. So a lot of investments are on their way to get the electricity from these renewable energy zones, which are more in the sort of outback of Australia, where there's plenty of sunshine, plenty of wind, to more the industrial areas. So those investments are certainly on the way, but I think we've got a couple of years of holding back of further growth in renewable energy because of the slow uptake of those investments, or they're still going to be a few years away. But when they come, I think we'll not be holding back investments in heat pumps and the like, that's for sure.
Okay, great, thanks. We have a question here, which is maybe for the Japanese presentation there. The question, which refrigerant was used for the heat pumps which could achieve heat delivery at up to 200 degrees? We had a question there.
Sorry, so this information is confidential. Now, this project ongoing by national project by NEDO. So this project will finish at the end of 2022. So after 2 years later, the refrigerant will be open. But so this refrigerant is new refrigerant. A refrigerant manufacturer, Central Glass in Japan, is developing a new type refrigerant. Thank you.
Watch this space, basically. More information in 2022. Okay, we have a general question here, and anyone who likes can handle that. Maybe all of you can handle that. Read this one up. What are the barriers related to increased use of high temperature heat pumps from the perspective of industrial decision makers? Is it a lack of knowledge about how to integrate those heat pumps into the existing processes? And are there concerns about future electricity prices? Who would like to provide some input there?
I'm happy to throw in a couple.
Yeah.
I think that one of the key things is integration is not simple. And we found that we had to train consultants about how to do process integration studies because they didn't know how to optimally integrate a heat pump. And ideally, you'd want to put in a heat pump into the design of the facility rather than to try and retrofit. Retrofit's always difficult, but we also found there was, in the Australian market at least, there was an enormous amount of ignorance about heat pumps in manufacturing. They weren't well understood, well known, and they were seen as being new technology and risky. And I think the other thing that the person mentioned was the uncertainty about future electricity and gas prices. That probably another factor. But we found the biggest problem was the complexity of retrofitting in existing facilities.
Yeah, there certainly was a lack of capability in a lot of energy consultants, engineering companies, of how to do pinch analysis and how to use that to optimize the heat pump design. We've seen some other basic areas as well. When you've got a capex cost some 8 times that of what a boiler is, then it becomes absolutely crucial that you size the pump perfectly, and just basics like not sizing it for peak loads, but making sure you incorporate thermal storage so that you can size the heat pump for average loads, not peak loads. So, but that requires a mentality change, because they're just used to a boiler being on demand. You know, whatever I need, it's there. So it does require some mentality change to think a bit more about thermal storage and integration.
Okay, great. Veronika, anything else
Yeah,
you'd like to add there?
I'd like to add that usually industrial companies ask for references and want to make sure that they really integrate established technology in their processes, especially if it's critical for production. So if we look at the very high temperatures where we are still in a demonstration phase, this is also a barrier that has to be tackled in the next years. And I think the investment costs is also can be very crucial if we look at industries that demand amortization times of 2 years, for example. Yeah. This is quite a challenge. And as you mentioned already, integration is not always straightforward and easy, especially when we think of discontinuous processes or complex installation with different options where to place the heat pump.
Yeah. Okay.
I think the future scenarios are really helpful for the heat pump, because I think it's not mainly the concern about the electricity price, but the concern that CO2 emissions might cost really a lot. I think this is something that's helpful for heat pump integration.
Provided the grid can provide that low carbon electricity, yes, of course. They have to go hand in hand.
Yes.
Yeah. Okay, I think we're moving to the end of our time, but let's see, Tor-Martin, since this was a very general question to wrap up the session, maybe we can go over to you and anything else you would like to add about these difficulties, barriers, your perspective on that.
Yeah, I think many of the barriers have been covered already. So in my experience, it's also the that you can show an operating case. We get a steady stream of interested people, so I don't think it's like lack of knowledge. And also at least in Europe, the electrification of the energy system is driving people to find ways how to use electricity more cleverly. So I don't think that's a problem either. But as it's new technology and the technology risk is at least perceived to be quite high. So if you have lots of installations, it's much easier to point to this is successful, and then it's much easier to also get people to install in new places.
Yeah, the usual problem, finding the early movers.
Yes, yes, exactly.
Okay, Takenobu, do you want to add anything there from your Japanese perspective?
Yes, I agree with other speakers. And the first barrier is the short payback period. In Japan, generally, customers needs in 3 years. So it's very high hurdle. So, and high temperature heat pump is a new technology. So we need to show the reliability and confidence from customers. So we need to share the actual application examples with many customers. Thank you.
Okay. Well, I think our time is up, right? We've even run over a little. I think most of us need time to stretch our legs before the next session starts. at 2 o'clock. So I would really like to thank all of our speakers. Been some great presentations, some really interesting papers, and some good discussion. So I think I will declare this session closed, unless there was one last question which popped up there. Okay, there was one last one. Let's take that one and then wrap up. Anyone aware of some good example of heat pump applications in the beer manufacturing industry? Anyone have a quick answer there?
Well, there's an example from Austria where they use a heat pump in to cool the fermentation process, and they use the heat to supply district heating. This is not, it's not really on the beer itself, but it's part of the brewery. So I think this would count as an example.
Beer making, yeah, okay, it's not the brewing part. But
yeah, but
the brewery premises,
yeah.
yes, okay.
So
yeah.
yeah, if someone is interested in that, yeah, we have a paper where this process is described a bit, so I can forward this information.
Okay, great. Australia, what brewing down there and heat pumps?
Yeah. A lot of interest. We've got to have steam producing heat pumps. That's the only problem.
All right. Okay. Great. Well, I think the questions are over now. So thank you all once again, and enjoy the rest of the conference, and hope we'll see you again in panel 4 and some of our other sessions. Bye for now.